You learned at school that the solar system looks something like this, right? Well, it seems all good, except there's just one problem. It's wrong. The sun is not the center of the solar system. The Earth and all the other planets don't actually orbit the sun. Now I know what you're thinking. Clickbait! Well, before you click off, just wait a second. Because in this video, I will prove to you that what you learned in school isn't quite correct. And how the truth might just be a whole lot more different than you might think. Okay, first up, what am I talking about? How can something which seems so obvious, and we learned we were like 6, be suddenly disproven? Well, like most things, we have to learn a bit of history. So, let's see. Wind the clock. Stop. Gosh, who edits these things? Oh, right. Back to the video. We won't be meeting any dinosaurs today, so let's stop right here. So, it's the mid-300s BC, and this is what everyone thinks the entire universe looks like. Just our solar system. That's because, back then, we didn't know about the Big Bang, galaxies, other planets, and all that stuff. And so, our universe was just our solar system. And this had been the leading idea for hundreds of thousands of years, and few had questioned its accuracy until much, much later. Also, you may have noticed that in this solar system, the Earth is in the center, because they believed all the planets revolved around the Earth and not the Sun. This is known as a geocentric universe, so they thought the Earth was the center, not the Sun. But would you have been able to tell the difference from Earth? What would you see? You look up into the sky. In our daily lives, we usually think of the sun moving across the sky during sunrise and sunset, rising in the east and setting in the west. The sun, moon, and stars all seem to move across the sky like this, and the Earth feels stable and unmoving beneath our feet. But what's actually happening is the Earth is revolving in space, and so the sky seems to be moving, but really it's the Earth. But we still use geocentric language today. Like when we say the sun is setting, we don't say the Earth's rotation is moving the sun away from me, even though it's not technically correct. Now, would we notice the difference from Earth? Probably not. And that's because we didn't have telescopes or anything back then, so we could only see using our eyes. So the difference would be between these two videos, which would be very hard to see. And you still can't prove it using eyes today. I mean, just look up at the sky and you'll see the Earth just seems still and not moving. And so back then, they imagined the Earth as not moving at all. And that's why it took a lot of convincing for this idea to be proven wrong. And that's all because of the Greek philosopher Aristotle. He was pretty famous back then, and he believed the planets and the sun all orbit the Earth in perfect circles. Well, I should say the word wanderers instead of planets, because they used to call them that, because they wander across the sky. The name planet comes from the term planetes to describe this later on. And like we said earlier, the Earth stayed still in this universe. And surprisingly, Aristotle knew the planets were round. He had observed lunar eclipses, noticed a round sphere on the moon, had seen ships sail away from the horizon. This guy wasn't messing around. Aristotle's idea seemed solid until people started to notice some mistakes, including the ancient Greek astronomer Ptolemy of Alexandria. He was the next major person to influence our understanding to this day. Now, Aristotle's idea had grown massive and was the most popular at the time. Other ideas, whether the sun was in the center and the Earth orbited the sun, like the one Aristarchus of Samos proposed, were ignored because of this. But this time, there was more proof. Ptolemy and many other astronomers had noticed that some planets, like Mars, seemed to sometimes speed up or slow down, and even go backwards. This is called retrograde motion. To make his observations match up with the model, change was needed. Aristotle's model didn't explain this weird way planets seem to move across the sky. He didn't change the entire model Aristotle had made, but made a few changes. First, he added these things called epicycles, invisible points that planets orbit while orbiting the Earth. These epicycles could help predict where planets will be in future. There's just one problem. They realized that they had to add more circles orbiting other circles for planets moving faster and slower at random points, and add circles to explain that, and well, you get the idea. It was incredibly messy and complicated. His model was just so excessively complex. Plus, the observations he made were also terribly wrong, and based on completely wrong assumptions. Also, why are all the planets orbiting nothing? Well, his model had its flaws, but it still solved the major problem, retrograde motion, except in a really messy and complicated way. I wonder, maybe, just maybe, could there be an easy way to explain all of this? Well, no. That wouldn't come until much, much later. Somehow, Ptolemy's model stayed for a while, mostly because of its ability to predict future astronomical events. And so, our solar system stayed how it looked like, with the Earth in the center for some 1,500 years. And then, in the 16th century, everything changed. The Polish astronomer Nicholas Copernicus and many others noticed that Ptolemy's model didn't seem to match the maths. The fix was, of course, to remove the Earth from the center and swap it out for the Sun. He had finally created a successful heliocentric model. Now, back in those days, most of these astronomical decisions and changes to models had to agree with what the Catholic Church agreed on. Now, Ptolemy's model and Aristotle's both had the Earth in the center of the solar system, but not Copernicus. So naturally, you would think that the Church would despise his model. But contrary to what you might think, they actually accepted his model, and not just that, praised it. At least for a while. Nobody had ever done something like this before. The idea of heliocentrism never stayed long like this. This was mostly because either he had a strong position with the church, or perhaps people had a change in thought. But, of course, there would be criticism. Waves of protests came through soon after, and the Catholic Church joined in too, leading to Copernicus's research, his papers, being banned in 1616. And only later on, after loads of evidence by countless other people and backing up, the ban was finally lifted in 1835. Now, this didn't come without some changes. Johannes Kepler solved retrograde motion by realizing that planet orbits weren't perfect circles, but rather ellipses, which explained the slowing down and speeding up of planets. Galileo used his telescope to observe the universe and found further evidence that supported heliocentrism. And that's how our understanding of the universe changed over time, and how the world we know today got accepted. Thanks for watching, make sure you like and subscribe, blah blah blah. See you next time. Hang on, didn't you say the sun isn't actually the center of our solar system? Yep, that's correct. The story isn't over yet, because even the heliocentric model we have today is wrong. This is because of what the next scientist in our story proved. Isaac Newton. Previously on Sat6, in my skydiving video, we covered how Newton's third law works. You can check that video out here, but here's a quick summary. In 1687, Isaac Newton published his groundbreaking paper, The Mathematical Principles of Natural Philosophy. In the paper, he described the relationship between the motion of an object and the forces acting upon it, using 3 laws. The third law famously states that every action has an equal and opposite reaction. Newton wrote, "Whatever draws or presses another is as much drawn or pressed by that other." Now this seems simple enough. Fish can swim forward because they push the water backwards, leading to the water propelling them forward. When you sit down, your body pushes on the chair, and the chair pushes you up with an equal force. Rocket engines expel hot gases downward, and the gas pushes the air upwards. I could go on. Newton's third law and all of them were really vital to the next era of scientific understanding. Now, Newton's third law is pretty easy to understand and work with, but if you consider all the implications and keep going down Newton's path, things get a little weird. You'll see why soon. Newton's third law also applies to other things like gravity. Say you throw a brick in the air, for some reason, then the earth would pull on the brick, but the brick will also pull on the earth with a minuscule amount. This is because any two objects with mass exert gravity on each other. People included, all of us as we stand are being pulled down onto the earth, and we technically pull the earth upward with an equal gravitational force. But why is this force unnoticeable? Why can't we see this? Well, the strength of the pull depends on the masses of the objects and the distance between them. Larger masses pull harder, and the closer the two objects are, the stronger they feel each other's pull. You don't feel or see the earth being pulled upwards because it's so massive compared to you, so this force is invisibly tiny. Newton's theory and his laws were overwhelmingly accepted for over 200 years and were very successful, mostly because they were quite accurate and still are today, and also because if physicists did try to argue with Newton and give him some action, they'd just get an equal and opposite reaction. Anyways, like I was saying, Newton's laws apply to everything, even large masses like the Sun and Earth. But we'll get to that later. For now, I want to talk to you about center of mass, because this will be important for later. Let's get into it. Every object has a center of mass, that exact center of all the matter an object is made up of. It is also the point in which an object can be balanced. Just like this ruler. This ruler's center of mass is directly in the center of it. Its mass is evenly distributed. However, this is not always the case. Take this mallet for example. Its center of mass is not located in the center of it, but rather all the way on this side. That's because most of the mass is located on the heavier end of the mallet, so its center of mass will be closer to the heavier end. Now this principle also holds true in space. In fact, it's the very reason why the Sun isn't the center of our solar system, and why the Earth doesn't technically orbit it. Because as the Sun's gravity pulls Earth around it, the Earth pulls back on the Sun by a small amount. So really, the Sun doesn't just stay still while the Earth orbits it, and that's because, in space, two objects orbit each other around their shared center of mass. This center of mass is known as a barycenter. You can think of the Sun as being the heavier side of the mallet. It's got far more mass compared to the Earth, in fact 333,000 times more. And the Earth is the other side of the mallet. The barycenter, just like the center of mass, is closer to the object with more mass, in our case the Sun. Think of this like a seesaw, the Sun on one side and the Earth on the other. Well, the barycenter would be the place on the seesaw where the Sun and the Earth perfectly balance. As we said, the barycenter is closer to the Sun because of its larger mass, so the balancing point is very close to the center of the Sun, but not exactly. So that's why the Earth doesn't orbit the Sun, technically. But this is only a small difference. What is the center of mass of the Sun in a bigger planet, like Jupiter? Jupiter is a lot larger than the Earth, with around 318 times more mass. So the barycenter of Jupiter and the Sun isn't in the center of the Sun. It's actually just outside the Sun's surface. Now this idea creates some strange things. Things you thought were obvious or elementary are now wrong. The Moon doesn't orbit the Earth. The Moon and the Earth orbit their shared barycenter, which is closer to the more massive Earth. In fact, all the planets exert a small pull on the Sun. So by factoring in all the masses, all the distances and forces, you get the gravitational center of the solar system. The center of mass of every object in our solar system combined. This is exactly what researchers did in 2020, pinpointing the barycenter of the entire solar system. And that also means the Sun isn't the center of the solar system. The gravitational center, the barycenter of our solar system, is.
So this means, as the planets orbit, the Sun also moves in its own little circle. The solar system's barycenter also moves, and changes position depending on where the planets are, usually moving from the center of the Sun to being outside the surface. Right now, in 2026, the barycenter is not inside the Sun. However, next year, it will be, for the first time in more than a decade. So what does this mean for us? Well, to be honest, not much. Life continues on for most people, completely unaware about all of this. But the effect is not completely useless. In fact, it's recently become quite useful for scientists in discovering new planets outside our solar system, called exoplanets. You see, if a star has planets, then the star orbits around a barycenter, not at its very center, just like the Sun. The star seems to wobble back and forth. Exoplanets are rather difficult to see directly, but this method of detecting a star's wobble is an efficient way to find out if any exoplanets are orbiting it. Many exoplanets have been found by astronomers because of this, and we have expanded our understanding. The Sun may not be the center of the universe, or the solar system, but it's still a very special place to us. The Sun is single-handedly responsible for all life on Earth, the reason all of us are here today, the reason you're watching this video right now. It holds all the planets in orbit. It provides the light and warmth every living creature needs. It's why we live in such a special, perfectly balanced planet. So it might not be the center of everything, but we should be grateful that we are so lucky to have it. Thank you so much for watching this video. If you made it this far, then you must like science. So if you could please like and subscribe, that would really support the channel and help fight the algorithm. Stay tuned for the next video and I'll see you there. Thanks again for watching. I also just wanted to give a quick shout out to these people for subscribing since the last video with the public setting turned on. Make sure to do that so you can get a shout out next time. Roll the credits.